Hello friends, welcome to my channel FS Studios International. So today I am posting the how did the solar system form. As my promise, I said that after 100 views I will upload a video on how did the solar system form. So here's the video, and make sure you like, share, subscribe this video. And I have created my own website, you can check out in the description. So let's go into the intro. So how did the solar system form? This credit goes to space.com and by Nola Taylor Reid. Thank you Nola Taylor Reid. He published this article at 4 years ago. So let's go into the video. So approximately 4.5 billion years ago, gravity pulled a cloud of dust and gas together to form our solar system. While scientists aren't certain of the exact nature of the process, observations of young stellar system combined with computer simulations have allowed them to develop 3 models of what could have happened so many years ago. So the next is birth of the sun. How did the sun form? So a massive concentration of interstellar gas and dust created a molecular cloud that would from the sun's birthplace. Cold temperatures caused the gas to clump together, growing steadily denser. The densest parts of the cloud began to collapse under its own gravity, forming a wealth of young stellar objects known as protostars. Gravity continued to collapse the material onto the infant objects, creating a star and a disk of material from which the planets would form. When fusion kicked in, the star began to blast a stellar wind that helped clear out the debris and stop it from falling inward. Although gas and dust shroud young stars in visible wavelengths, infrared telescopes have probed many of the Milky Way galaxy's clouds to reveal the natal environment of other stars. Scientists have applied what they've seen in other systems to our own star. After the sun formed, a massive disk of material surrounded it for around 100 million years. That may sound like more than enough time for the planets to form, but in astronomical terms, it's an eye blink. As the newborn sun heated, the disk gas evaporated quickly, giving the newborn planets and moons only a short amount of time to scoop it up. Formation models. Scientists have developed 3 different models to explain how planets in and out of the solar system may have formed. The first and the most widely accepted model, core accretion, works well with the formation of the rocky terrestrial planets, but has problems with giant planets. The second, pebble accretion, could allow planets to quickly from the tiniest materials. So quickly form from the tiniest materials. The third, the disk instability method may account for the creation of giant planets. The core accretion model. Approximately 4.6 billion years ago, the solar system was a cloud of dust and gas known as a solar nebula. Gravity collapsed the material in on itself as it began to spin, formation the sun in the center of the nebula. If you want another video on a nebula, please give 5 likes. With the rise of the sun, the remaining materials began to clump together. Small particles drew together, bound by force of gravity into larger particles. The solar wind swept away lighter elements such as hydrogen and helium from the closer regions, leaving only heavy, rocky materials to create terrestrial worlds. But farther away, the solar winds had less impact on lighter elements, allowing them to coalesce into gas giants. In this way, asteroids, comets, planets, and moons were created. Some exoplanets observations seem to confirm core accretion as the dominant formation process. Stars with more metals, a term astronomers use for elements other than hydrogen and helium, in their cores may have more giant planets than their metal poor cousins. According to NASA, core accretion suggests that small rocky worlds should be more common than the more massive gas giants. The 2005 discovery of a giant planet with a massive core orbiting the Sun like star HT 149026 is an example of an exoplanet that helps strengthen the case for core accretion. Don't skip this video from here. This would be interesting part. This is a confirmation of the core accretion theory for the planet formation and evidence that planets of this kind should exist in abundance, said Greg Henry. In a press release, Henry, an astronomer at Tennessee State University, Nashville, detected the dimming of the star. In 2017, the European Space Agency plans to launch the Characterizing Exoplanet satellite CHEOPS, which will study exoplanets ranging in sizes from super Earths to Neptune. Studying these distant worlds may help determine how planets in the solar system form. In the core accretion scenario, the core of a planet must reach a critical mass before it is able to accrete gas in a runaway fashion, said the CHEOPS team. This critical mass depends upon many physical variables, among the most important of which is the rate of planetesimal accretion. By studying how growing planets accrete materials, CHEOPS will provide insight into how worlds grow. The disk instability model. The need for a rapid formation for the giant gas planets is one of the problems of core accretion. According to models, the process takes several million years, longer than the light gases were available in the early solar system. At the same time, the core accretion model faces a migration issue, as the baby planets are likely to spiral into the sun in a short amount of time. Giant planets from really fast in a few million years. Kevin Walsh, a researcher at the Southwest Research Institute SWRI, that in Boulder, Colorado, told Space.com, thank you Space.com, that creates a time limit because the gas disk around the sun only lasts 4 to 5 million years. According to a relativity new theory, disk instability, clumps of dust and gas are bound together early in the life of the solar system. Over time, these clumps slowly compact into a giant planet. This planet can form faster than their core accretion rivals, sometimes in as little as 1,000 years, allowing them to trap the rapidly vanishing lighter gases. They also quickly reach an orbit stabilizing mass that keeps them from jet marching into the sun. As scientists continue to study planets inside of the solar system as well as around other stars, they will better understand how gas giants formed. Don't skip from here. This part is also very important and interesting. Pebble accretion. The biggest challenge to core accretion is a time building massive gas giants fast enough to grab the lighter components of their atmosphere. Recent researchers probed how smaller pebble-sized objects fused together to build giant planets up to 1,000 times faster than earlier studies. This is the first model that we know about that you start out with a pretty simple planets from and end up with a giant planet system that we see. Study-led author Harold Levison, an astronomer at SWRI, told Space.com in 2015. In 2012, researchers Michael Lambrecht and Anders Johansson of Lund University in Sweden proposed that tiny pebbles, once written off, held the key to rapidly building giant planets. They showed that the leftover pebbles from this formation process, which previously were thought to be unimportant, could actually be a huge solution to the planet forming problem, Levison said. So what did Levison said? Let's see it. Levison and his team built on that research to models more precisely how the tiny pebbles could form planets seen in the galaxy today. While previous simulations, both large and medium-sized objects consumed their pebble-sized cousins at a relatively constant rate. Levison's simulation suggests that the larger objects acted more like bullies, snatching away pebbles from the mid-sized masses to grow at a far faster rate. That's all for this video, because this video goes long than 10 minutes, and I will make part 2 after this goes 20 views. After 20 views I will confirm make part 2 for this, and make sure you